involve areas, then you use a quadratic polynomial, or problems involving volumes, then you're going to use a cubic polynomial. But now suddenly polynomials were being used for interpolation. They're being used to approximate the missing values in a table. And once you start doing that, there's no reason to stop at polynomials of degree 3. There's no reason to stop with volumes. The Greeks stopped with polynomials of degree 3 because it made no sense to talk about a four-dimensional region. But if you're simply looking at the interpolation, suddenly it makes sense to go beyond degree 3 and consider a polynomial of degree 4, a polynomial of degree 5, a polynomial of degree 6. And we're not entirely sure where these different polynomials came from, but it seems that this was one of the important sources of the development of the idea of a polynomial of general degree. Also, the Diophantine equation that was studied by Brahmagupta, this general problem, you've got a perfect square, and you subtract some integer times another perfect square. I gave the examples where it's a perfect square minus 8 times another perfect square equals 1, or a perfect square minus 61 times another perfect square is equal to 1. That is known today as Pell's equation. And this is an equation that was not just studied by Bhaskara. Bhaskara actually was able to find a way of coming up with a solution to Pell's equation no matter what multiplier you were using. So you could use an 8, you could use a 61, you could use any number as long as it's not a perfect square. So you could take x squared minus 57y squared equals 1, or x squared minus 327y squared equals 1. And Bhaskara laid out a procedure that would enable you to find a pair of integers that would then satisfy that equation. Indian mathematics would continue after the fall of Ujjain. Ujjain disappears in 1235. This is when the Delhi Caliphate conquers Ujjain. The astronomical center is destroyed. At that time, at the time of the conquest, the astronomers in Ujjain are dispersed. Northern India ceases to be a center of important mathematical work, but the mathematical work of that time does move down into southern India, specifically southwestern India in Kerala. And we do have a series of important Indian astronomers doing work in mathematics down in Kerala, beginning with Madhava in the 14th into the early 15th century, Parameshvara, late 14th century into the 15th century, Nilakantha, 15th into the early 16th century. And what these astronomer mathematicians were able to do is to take the general idea that Bhaskara had done of taking a trigonometric function, looking at its rate of change, and using the rate of change, and the rate of change of the rate of change, and the rate of change of the rate of change of the rate of change, to come up first, as Bhaskara did, with a quadratic polynomial that's a good approximation to the sine function, and then a cubic polynomial, and then a fourth-degree polynomial, and eventually they saw how to get a polynomial of arbitrary degree. So you can get a polynomial of as high degree as you want. The higher you take the degree, the closer the approximation is going to be. And it's not clear which of these astronomers actually was responsible for it. It's generally believed that this goes back all the way to Madhava. But at this time, what they did was not just figure out how to get polynomials of arbitrarily large degree, they then made the jump to a polynomial of infinite degree, what today we would call a power series. So this is an infinite collection of powers of your unknown, which can be brought as close as you wish to the actual value of the function. So it's a representation of the function as a sum of powers of the unknown. The powers go out toward infinity. You can get as close to the value as you want just by going far enough out. This is work that was probably done in the 14th century. This is work that would not be redone in Europe until the very end of the 17th century. Unfortunately, the work that was done in India was lost to the rest of the world. The astronomers who were working on power series in South India were not able to communicate their results to anyone else. And the fact is that their way of approximating the sign was almost too accurate. The problem was that you can only measure the difference between two lights in the sky to within maybe a couple minutes of arc. So being able to calculate values of the sine or the cosine or the tangent to this kind of accuracy was far more than what was needed. And at this point, nobody could figure out any other uses for the sine or the cosine. The only uses for these trigonometric functions at this time was in astronomy. And since no one could figure out these uses, eventually knowledge of these power series would be lost. And it was only in the 19th century, actually, when British archaeologists managed to come across some of these old documents from several hundred years earlier. Mathematicians then looking at them realized what actually had been accomplished. But it points out the importance of not just pulling ideas from the world around you. The ideas that you pull out of the world around you have got to be applicable to worthwhile problems in understanding the world. And once the mathematics becomes divorced from what is really needed, there is the danger that it's going to degenerate. In the next lecture, I'm going to move north from India into China, and we will see what was happening at this same time, the first millennium AD, roughly up to about 1300 AD in China.